Alrighty, so with this video, we're going to do a little exam review for the first test in our circuits class. Obviously, I think all of you have had me in previous classes, so you know what my tests are like. This won't be any different. 5 questions or less, probably fewer, all calculation-based, and I'll show you with some examples that we go over in this video what to expect more explicitly, but basically it's covering all the topics we've done thus far in the semester, and I'll go ahead and list them. So the first, of course, is calculating the total or the resistance of a circuit. Usually the total resistance, but even if we're talking about some little part or component of a circuit, what's the resistance of that little part of the circuit? Same kind of a thing. So what we know is that generally in a circuit you have your resistors. Those resistors can be connected in different ways. The ways we'll worry about, at least for now, they can be connected in series or in parallel. So in series, you basically have a circuit that kind of looks something like this. We have a resistor, something like this. Nice basic circuit. This is the voltage source. Let's say this is resistor 1, this is resistor 2. These two resistors are connected in series, and the way I know it is several ways you could imagine it. The first intuitive way is to look at how the current would be flowing through this circuit. So let's say we have some current flowing in a clockwise direction. Current's going to hit this resistor, go through the resistor, continue along, hit this resistor, and continue along like that. And the fact that the current that flows through resistor 1 has no choice but to also go through resistor 2, it can't divert to another branch or something like that, we know these two resistors have to be in series. The other way of thinking about it is to look at the nodes. So if we put a little dot on either end of every element in our circuit, we'll call those nodes. We know that two resistors are connected in series if they share only one single node in common. So with these two resistors, they share this node in common, but this node does not touch resistor 1, and this node does not touch resistor 2. So these two resistors share one node in common, thus they're connected in series. Why do we care? Well, if resistors are connected in series, then we can calculate the total equivalent resistance. So that is to say, we can redraw this circuit with only one resistor whose resistance, we'll call R series here, is the same, or that is to say, it affects the current running through this circuit the same way that the original circuit affects the current. So this circuit here is an equivalent circuit, meaning it acts the same as our original circuit, but it's simplified. Instead of having two resistors, it's just got one resistor. And so what we would want to do is figure out what is the resistance of this new equivalent resistance, this new equivalent circuit's resistor. And it's very easy. If we want to know the total resistance for resistors that are connected in series, it's just the sum of each of the resistances. Or if I write it out, it's just R1 plus R2 plus R3 and so on for as many resistors as is connected in series altogether. We just add them all up, just how you would imagine you would find the total resistance, and that would be the resistance of a single resistor placed in place of the other resistors that are connected in series. So all of these resistors act as if it's a single resistor with this resistance. Now the other way that the resistors can be connected is parallel. And so what does this look like? Here's an example. We could have something that looks like this. So again, we have a voltage source, we've got some R1 and some R2, just like the other circuit, but these are connected differently. These are parallel, and the way I know, again, going back, I have two different ways of looking at it. The first way is imagine the current. We're going to have the current flow clockwise again. So the current is coming up from the voltage source. It hits this node right here. And at that point, the current can kind of divert. Some of it can go one way, some of it can go the other. It doesn't all have to go one way. And so you get some amount of current going to that branch and some amount of current going to that branch. Then they get past their little resistors, this guy comes down, and these two currents meet back up at this point, and then continue along the circuit as usual. So here, if you notice, resistor 1 has some amount of current, this amount going through right here, and then after it gets to the resistor, it hits this node right here and just continues down as usual. Notice that current does not hit resistor 2. Likewise, this current is hitting resistor 2. After he hits him, he continues on, hits this point, and then continues on with joining up with the other current. So notice that amount of the current goes through R2, but does not go through R1. So whatever current goes through one of the resistors, it doesn't have to, and indeed it does not, go through the other resistor. Because of this, these two resistors are connected in parallel. Okay. The other way of thinking about it, the nodal analysis way, is let's go ahead and put a little dot on each node on either end of every element in our circuit. And now here's a little rule we need to worry about. When I'm putting these nodes, notice for our series circuit over here, this node here is placed between the voltage source and resistor 1. This node right here is placed between resistor 1 and resistor 2. And then this resistor, bottom right, node, is placed between R2 and the voltage source, but so is this one. Both of those nodes have R2 on the right side and a voltage source on the left side, and nothing in between, just the wire. So in actuality, these are really the same node. That is to say, it's as if it's the same point on my circuit. I show a bunch of wire there, but that's just because that's how I drew it. So if we look at the parallel circuit, we have a similar thing. Notice over here on the left, this node and this node, there's nothing between them but wire. So really they're the same node. And then over here, this node here, this node here, this node here, and this node here, believe it or not, are all the same node basically. But for now, we'll just look at it like this node and this node. Now, here's the rule. In series, if two resistors are both share a single node, that's series. For parallel, if two resistors share two nodes in common, that's parallel. So here, of course, we see R1 and R2 share that node and this node in common. They share two nodes, thus they are in parallel. Now, just like with the series, if we want to combine these resistors as if it's a single resistor with the same effect as this combination, what would that, so if I draw it just like before, we want to draw this kind of a circuit with some RP such that that resistor acts the same way as the original one. Well, the equation for this one is not as easy as the series one. Here we have to say it's 1 over the total parallel resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. So unfortunately, we don't just add the resistances, we actually have to add the inverses. Okay, and then the big thing to remember, we have to flip our answer because we don't want 1 over R parallel, we want R parallel. So at the end, after you add up all these 1 over things, you just take 1 over that answer because you want R parallel. So that was adding resistors in series and parallel. Whether there will be a question specifically on this, I don't know yet, but certainly you need to know how to do this for all the other circuits anyway. So even if I don't have a question that's just, hey, what's the total resistance, you're going to have to do it when I do an Ohm's law question or nodal analysis or whatever. All right, so speaking of that, the next big topic was Ohm's law. And so this was given a circuit with some set of resistors that might be connected in series, might be connected in parallel, something like this. I want you to fill in this kind of a table. Oops. R, I, B. So let's say this is R1, this is R2, this is R3, and this is our voltage source. So for R1, R2, and R3, I want to know what is the current running through the resistor and what is the voltage dropped by the resistor. So this is how all the questions on the test are going to look. You're given a circuit, fill in the table. Now, how do you go about doing this under Ohm's law? Well, Ohm's law says the voltage is equal to the current times the resistance. And this means not just the total voltage on a circuit is the total current times the total resistance, but also the voltage on R1 is equal to the current going through R1 times R1. So that is, let's say I want to know what's the current running through R2. If I know the voltage that's dropped by R2, and I know R2 itself, well, I could find the current just by doing V equals IR. But you could also do it for the whole circuit. So calculate the total resistance of the circuit, then you could get the total current, and then go from there. So that's your main equation. Along with it, you use other facts like when two resistors are connected in series, each one will drop a different amount of voltage based on its resistance. A higher resistor will drop more voltage than a smaller resistor. But the current that runs through each is the same, because as we saw in these examples for series, if the current goes through R1, and R1 and R2 are in series, then that same current has to go through R2 as well, by definition. So for series, voltage different, current is the same, and then in parallel it's the opposite. In parallel, each branch of the parallel piece will drop the same amount of voltage, and by the way, that's the same as the total voltage drop by the whole parallel piece as if it's a single resistor. But the current that goes through each branch is different. If you have two resistors connected in parallel, more current will flow through a smaller resistor side than the larger resistor side. Just like you would imagine water flowing through pipes or whatever, the thing wants to go through less resistance, so more current will choose the smaller resistor path. So in parallel, the current is different on each branch, but the voltage is the same. All right, third topic, loop analysis. So this was given some circuit, maybe something like this. This is the standard example I like to give. R1, R2, R3, voltage 1, voltage 2. So given a circuit like this, again, I want to find all the values and compute for R1, R2, and R3, just like before. But now we see we have some issue. We don't just have a bunch of resistors, now we have a second voltage source. So that's going to complicate how we go about trying to solve it, at least using just basic Ohm's law. So we use loop analysis for this, and the way we think about it is we have two loops in this circuit here, the left loop and the right loop. And so what we're going to do is we're going to assume there's some current I1 flowing around in this loop and some other current I2 flowing around in this loop. Now, I've chosen the current to flow clockwise. They may not. Maybe one of them flows counterclockwise. It turns out you could choose either direction you want, and if you happen to have gotten it wrong, your answer will just come out negative. So that's not a big deal. So just easiest way is just always choose clockwise, and then if you get a negative answer, you know, oh, it actually went counterclockwise. But if you want to think about it, you know, the fact that this voltage source is pointing upwards probably leads me to believe that the current wants to flow counterclockwise there. But it doesn't matter. Just choose one and you're good. Once we've chosen that current is going to flow through these loops, we now use the actual loop equation, which says that if I add up all the voltage changes in a loop, it better be equal to 0. So let's say for loop 1, I'm going to have some voltage changes. Voltage sources can give me voltage or lose voltage. Resistors will always lose voltage because they're using it up. And so I want to make an equation of each one of the voltage changes, add them all up, set it equal to 0. So if we look at the first loop, the loop on the left, following the current, I first hit on the left the voltage source. And the way I hit it is I hit the small side then the big side, so I take that to mean I'm gaining voltage. So I gain V1 amount of voltage, whatever that number happens to be. Then I continue on, and then I hit R1 up there on the top. Well, every time I hit a resistor, I'm going to lose voltage. So I'm going to subtract off the voltage that's dropped by R2. But I don't know this number. However, I do know Ohm's law, so the voltage dropped by R1 is going to be V equals IR, I1 times R1. The current that's hitting the resistor times the resistance. All right, then I continue on, and then I go down here and I hit R2, so I'm going to drop a certain amount of voltage. How much voltage do I drop? The current hitting R2 times R2. But here's the issue with R2. That resistor is being shared by both loops. So there's some amount of I1 that's going to hit it and some amount of I2 that's going to hit it. They're both hitting it. So I have to add the total contribution. So I'm going to add these two currents. However, notice that I1 flowing in the clockwise direction, when it gets to R2, is going downwards. Whereas for I2 in the right loop, if I follow him, going clockwise again, when he gets to this branch, he's flowing upwards. So these two currents go opposite to each other, so they're going to interact. You're going to get less total current, and so when I say we're adding the currents, one of them happens to be negative because it's going the other way, the wrong way. So how much current is there? It's I1 minus I2. Again, if they were both going down, then it'd be I1 plus I2. But because I2 is going up, when I1 is going down, I2 gets a negative. So that's the current that hits R2 times R2, and that's the voltage. All right, we've gone past R2, we continue along, nothing, and then I get back to the voltage source, so I've done my whole loop, set it equal to 0. And now we'll know V1, we'll know R1, we'll know R2. but we don't know I1 and I2. So I've got two unknowns in this equation. Well, I can't solve two unknowns with only one equation, so I have to do another equation. This equation, of course, is for loop 2. And we do exactly the same thing. I'm going to follow the current around the loop. So I hit the voltage source, but I hit the big side, then the small side, so that's backwards, so I'm subtracting that amount of voltage. Then I continue along, I get to R2, so I'm subtracting. How much? Well, I2 is going up, I1 is going down, but I2 now is the positive direction, so it's I2 minus I1, hitting R2. Then I continue, go up to the top, and now I'm hitting R3, so minus the amount of current that hits R3, which is I2, times R3. Then I continue, get back to the voltage source, my complete loop. And so again, what do I know? I know V2, I know R2, I know R3. I don't know I2, and I don't know I1. Two unknowns. But now, two equations, two unknowns. So now I just use my algebra techniques, whatever algebra I want to do, calculate my I1 and I2. Once I know these two, I could start filling in the table. Because what's the current hitting R1? Well, it's just I1. What's the current hitting I3? It's I2. What's the current hitting R2? Again, it's I1 and I2 are both hitting it, but they go in opposite directions, so I subtract them. I1 minus I2. And then you get V from V equals IR. So that's loop analysis. Last, nodal analysis. So nodal analysis is a very, very similar technique. We're going to have some circuit. Let's say we have this circuit here. There we go. V1, R1, R2, R3, V2. All right, so again, what do I want to do? I want to fill in my table. I want R1, R2, R3, and I want the current and the voltage for each. Well, we could use loop analysis for this. Perfectly fine. However, a different technique we could try to use is nodal analysis. How does it work? Well, first of all, it's called nodal analysis, so it's going to have to do with nodes. So if we look, the most important node I see is this one right here. Yes, there's a node here. There's a node here. And then, of course, this is one big node down here. But we'll see why the green node is the important one. So in fact, I'll call it node A. Now here's the rule. The rule for nodal analysis is that at every node, there's going to be a bunch of wires coming in and coming out. And so there's a bunch of current either coming in or coming out. And the rule is whatever current comes into a node must leave a node. You can't have a buildup of current. So what we're going to do is we're going to make equations for the current coming into or going out of a node, add them all up, set it equal to 0. Okay, loop analysis, we make an equation for the voltages going around our loop, add them all up, set it equal to 0. Very similar, but now we're doing it for the current. Now, the reason I say these yellow nodes are not important is if we look at what the current's doing, so there's some current coming in and then coming out. There's just nothing there. It's just wire. So that's not an interesting node. And the same thing here. Maybe we have some current coming in like this and coming out of the node. Nothing interesting is happening. But at A, we've got some interesting stuff. We've got 3 different branches here, so current can go in different directions now. So we're going to say, okay, let's say we have some current coming in at A, and we'll call this one I1. And then maybe there's current leaving A going down. we'll call that I2. And then maybe some current coming in from the right, and we'll call that I3. Now, whether they're coming in or coming out, I'm just guessing. And again, just like with the loop analysis, if you guess the wrong direction, you'll just get a negative answer somewhere. So don't worry about it. I'm going to guess these directions and just go with the flow and see what happens. All right. Next thing we got to worry about is all the calculations we're about to make are going to be with respect to some reference starting point, some base level. So I'm not necessarily going to be finding the actual values of things, but rather how much more there is here rather than there. So think about if you have pressure in your tire, air pressure, then you get a flat tire, all the air gets pumped out of your tire. You put a little pressure gauge in, the pressure gauge says there's 0 pressure. But we know that's not really true. The pressure of the atmosphere is pushing on the tire. But the pressure of the atmosphere is pushing on everything. So all that really matters is the difference in pressure. How much more pressure or less pressure is there than the norm? And the same kind of a thing is going to happen here. We're going to assume the voltage somewhere on the circuit. And then all of our calculations are going to be compared to that voltage, this is 10 volts higher, or this is 5 volts lower, or whatever. So I'm going to choose, and usually it's like this big supernode down here with nothing interesting going on. I'm going to say there is a ground there. And a ground just means I know the voltage is 0 at this point. And again, it might not actually be 0. It might be something. But what I'm calculating is the voltage at this location, or the current at this location, is this much relative to that point being 0. Okay. So we need to make our equation. We have it all set up. How does the equation go? Well, this is on node A, because I might have other nodes that are important in other circuits that are more complicated. But for this node, I'm going to add up all the currents. And the rule I'm going to use is that if a current comes into the node, I say it's positive. And if it leaves the node, it's negative. So for node A, I've got I1 coming in, plus I3 coming in, and I2 coming out. And that's equal to 0. All right. Well, I don't know any of these numbers. So just like with loop analysis, when I didn't know the voltage, I turned it into IR. How? I don't know the current, so I'm going to turn it into V over R. So I need what is the voltage, which is at this location, or basically the change in voltage, the change in the potential, for I1. Well, I1, what did it do? It went through this resistor R1. So the resistor R1 is what changes the voltage. So the voltage for I1 is going to be V1 over R1. Okay, well, not V1, I better be careful here. I'll call it VA, V little a. And then for I3, what do we have? Well, it's going to be VB over R3, whatever the voltage is, and I'll discuss that in a bit, over his resistor. And then for I2, we get a negative because it's leaving, and it's going to be, let's say, VC over R2. All right, so I just changed all my I's to V's over R. That's it. Now the interesting part. This VA over R1. Let's look at what's happening. When the current goes through R1, notice the left side of the resistor over here, there's some amount of voltage. Then as the current goes through R1, it loses some voltage. So now the voltage here at A is some different number. You had V1, you lost it, you lost some of it because of the resistor. Now you're at some new voltage. So this little VA that I wrote here, this thing right here, what is that? I'm going to say it's the difference between where I came from and where I am now. So I1 is coming from V1 and going to A, so I'm going to say it's, where did I come from? V1. Where did I get to? Minus VA, capital A, that's the voltage at this location A, divided by R1. Again, let's look at the next one and see if we could get it from this one. For R3, notice this I3, it's coming from the voltage source V2, right here. It's going through R3 and getting to VA. So that voltage is going to be the difference between where I came from and where I got to. I came from V2, I got to VA, and I had to get through R3 to do it. Okay. Now the last one, VC, same kind of a thing. Here's I2 going down, it goes through resistor 2, and it gets to the ground. So what's his voltage? The difference between where I came from and where I got to. Well, I came from VA. Where did I get to? I got to the ground. And the ground I know is V equals 0. What did I have to go through? I had to go through R2 to do it. Set this equal to 0. And now what do we have? We have an equation. We know R1, we know R3, we know R2, we know V1, we know V2. All of these are numbers given in the problem. So we only have one unknown, VA. So this is the equation. Calculate VA. You now know what is the voltage at A. How does that help me? Well, once I know the voltage at A, if I want I1, which is the current that goes through R1, well, I1 is just V1 over R1. What was V1? Not V1, I should call it little VA again. VA was V1 minus V capital A over R1. Well, I now know what VA is. I already knew what V1 was. I already knew what R1 was. So this is a number. I now know the current, and that's what goes here. And then similarly for R2 and R3. So, nodal analysis, just like loop analysis. With a loop, you set up equations, one for each loop, and the equation is for the voltages. If you gain voltage, you add. If you lose voltage, you subtract. I replace the voltages going through a resistor by I times R. And then I solve for my I's. Nodal analysis, I have an equation for each node. The equations are for the currents, current coming in versus going out. If I come in, I add. If I go out, I subtract. I then replace all the currents with V over R, where V is the difference between the voltage I came from and the voltage I got to. Solve this for your V, and then you can fill in the table from there. And those are the topics. So certainly you're going to have at least one of each, probably 2 loop, maybe 2 nodal, and an Ohm's law, something like this. We'll see. But expect something like 5 or 6 questions. These 4 topics. Again, the first one, resistance, that's kind of tested with Ohm's law. But the whole point is, given a table like this, can you fill in all the missing values? You have to use these different techniques to find them. All right, and as usual, if you have any questions, feel free to email me, come by office hours, things like this. But I wish you luck.